coming back to it, this is our Hackaday quantum computing page. This is where you can find the slides, and I post the recording link here. And the thing that I'm also asking people to do is you can make comments and send questions here. If your questions that you post in the message here do not get answered, just come to Hackaday page. I have noted down some of these questions from last class. Some of them I've already answered, but some of them I may come back. I may address them in the class or make further comments to describe the answers. So thanks, Edward, for posting a question here. So let's come back to the slides. And I think we've already seen that Zoom is not quite good at collaboration. Let's just ask questions in the chat and not to interrupt the class. I want to give people some recap from last time, and also for some first timers, this may be helpful. Last time we talked about what qubits are and superpositions. In general, you can imagine all kinds of quantum systems with all kinds of probabilities. They would just add up in a linear combination that's called superposition. So here we are seeing one qubit that is 0 or 1 being in superposition with an amplitude A and B. The amplitude here has a significance that when you have a square of the amplitude, it means the probability of that incidence. 0, for example, A square means how much of 0, the probability of that state being in your system. This is a recap to just show you some of the examples that quantum state is a representation of probabilities. And the significance of amplitude here really gives us the opportunity to understand measurement. So let's delve a little bit of the amplitude here again. I've shown here several different numbers of qubits. If we have 1 qubit, that means your system could be in 0 or 1. The probability of 0 or 1 is given by the amplitude A and B here. A and B can be any number. It could be positive, negative, or complex numbers, as long as their square is their magnitude squared, summing up equal to 1. From this pie chart, you can easily see that the probability needs to add up to 1. So the area together form a circle. If you have 2 qubits, then there are 4 possible configurations you can put your 2 qubits in. It could be both qubits could be 0, or both of them could be 1. But we also have the case that one of them could be 0, one of them could be 1. So in total, we have 4 possible configurations. To represent the full state, you write out all 4 possibilities with weight, amplitude, A, B, C, D. Again, you are summing up the squares, each of them to get a 1. If you have 3 qubits, same thing, but then you are having 8 different possible configurations. So what this is telling us that as the number of qubits increase, if we have number n qubits, then there are 2 to the n possible configurations in your system. This is very powerful. Instead of classical computing, classical bits, where you have to represent every single state with a bit, here you have a superposition of all those possibilities. You can even just shorten your writing to a summation of all the configurations, all the possibilities. Here we see that the number of configurations scales as the number of qubits with 2 to the n, but also there's infinite numbers of possibilities for these amplitude. This is one of the most powerful things about a quantum bit, is that it's got all of these possibilities all in superposition together. And they all exist. If you were to describe it with a classical bit, you would have infinite number to describe them. And we started using the Dirac notation. I haven't really introduced it, but that was that symbol there, vertical line and your state plus a bracket. But I want to show you where it first came from. It's named after Paul Dirac, one of the greatest physicists who contributed in quantum computing in the 60s. That during that time, it was when quantum mechanics was just starting. Physicists back then were only familiar with classical systems. When they observed quantum behaviors in experiments, they found them very, very strange, and they didn't know why those results came about. However, they could write down, they could try to capture them with equations. So this Schrödinger equation describes a quantum system. If you look at the form of the Schrödinger equation, you know that this is a wave equation. A solution to the wave equation is a wave function. If you look at this form here, that's what I showed earlier. A summation of all the possibilities, all the possible wave functions. Together, they form a solution to this Schrödinger equation here. And Dirac came up with this notation to shorten how we write it, because otherwise you have to represent your coefficients and each wave function in a very lengthy wave function notation, and there's overlap integrals involved, is very lengthy. But he just wrote out, okay, so this whole thing will represent a state. And the coefficient, you can get it from the overlap integral of that particular state with the overall state. This is a little bit of physics, and we won't be using it very often. So I just wanted to mention this for people who know about the quantum mechanics, Schrödinger equations, to see the significance of a qubit compared to a wave function here. This notation is called kit. So this is part of a bracket notation. This whole thing is called bracket. The beginning, this one is called the bra, this one is called kit. So together they mean a integral. So not so much of wave functions will be needed, but for people who learned a classical way of learning quantum mechanics, this is how they relate. But I want to go back to the importance of amplitude. Where else have we learned about amplitudes? We've experienced it every day in waves. Water waves, sound waves, light waves, they all have amplitudes, and electrical waves that we detect on oscilloscopes. You've seen a lot of these. We know that amplitudes, if they have the same sign, if they point in the same direction, they add up. So the amplitude of two different waves, if they are constructively interfering, they would be adding up. But if their signs are pointing in opposite directions, they will cancel each other out. This happens in our quantum mechanics. And essentially, that is what we observe every day. So let me give you an example of how the amplitude is a significant quantity in quantum mechanics. So classically, if you want to represent probability, you just write out the probability. So say, I want to know if it's raining or sunny the day after tomorrow. If we were in a classical system, you just draw out the tree diagram and you multiply down all the probabilities. So sunny, you have 2 paths to get sunny. There's 50% tomorrow being sunny can split into 2 outcomes with I'm just giving random numbers here, 30% of being sunny and 70% of being rainy. You time these two. Plus, the other option is first getting rainy and then go to sunny. So in this case, you get 60% of likelihood that tomorrow, the day after tomorrow is sunny. However, if you were in a quantum system, the probability is not what we use directly. We use amplitudes, the coefficients that we put in front of the states. So we take a square root of these numbers. But then because amplitudes, we don't have any requirement of their signs. As I mentioned earlier, it could be positive, negative, or even complex numbers. For the sake of proving this, I'm just randomly assigning a minus sign here and see what happens. What you need to do is first time down the amplitudes and then take a square of the whole summation. But then because of this negative sign here, this path of getting a sunny day is interfering with your first paths. It actually subtracts with that and reduces the probability of getting sunny day. So this is very strange. It is showing that in the quantum system, having more paths to get to the answer you want could lead to a reduction of its likelihood. This is very strange. It's very different from what we are used to in classical case. Essentially, what we observe in a quantum system is what the most possible outcome is that comes out of a constructive interference. So I think this, maybe seeing it the first time, is not very easy to absorb, but think about it more after this class, is that there could be an interpretation of measurements in quantum mechanics being we have all kinds of possibilities existing, but what we see is the outcome from constructive interference, because the destructive ones get canceled out. So just making an analogy, the very fact that we are sitting here talking about quantum mechanics could be a constructive outcome of the other possibility that we might be somewhere else. An obvious direct manifestation of this quantum interference is the double slit experiment. So for some people here, they may be familiar with this. Double slit experiment tests out how a beam of electron can land on a particular place after going through some slits. If you just have one and you block one of them, there's common sense that most of the electrons will land near this slit. So this is plotting the probability here. But if you open this other slit, you have two slits. Some people may think, oh, I would just have an additional another peak here. But in fact, it doesn't do that. What we see is a peak in the middle, and then the places where we may expect more electrons to exist, they actually don't have that many electrons. This spectrum is caused by interference. And this is a very direct manifestation of interference, and interference causes the result of our measurements. So superposition is enabling this strange behavior of quantum interference. It also enables something else, but we'll see it next time. And when we talk about measurements, we also should know that it's not reversible. So a spinning coin could be like our qubit that has possibilities of landing on head or tail. We don't know where it lands until we make a measurement. So in this case, measurement could be when we push it down. It will land on one of the sides. And a lot of older ways of explaining measurement is collapsing. You might have heard of this term, collapse or projection. And that is the Oppenheimer interpretation. Oh, sorry, that's called the Copenhagen interpretation. But now I think a lot of people are starting to adopt this many worlds interpretation, where interference is the actual mechanism that goes in here. But of course, projection or collapsing, it seems easier. So if you start with 2 qubits that will have 4 possible outcomes, when you do a measurement, say you are measuring the first qubit, if the result is 0, you would know that your state will be in either this 0, state or 0, 1 state. So you get rid of the other 2 because it's not possible from those other 2 states. Then you get a probability of these 2 coefficient magnitude square adding up. And after the measurement, your state, people say collapse, but really it's just you're getting the result of these 2 outcomes. Some good material to read further is from Scott Arison, these generalized probability theory, where he gives pretty interesting explanation why our world functions with amplitude square instead of just the probability. So classically, the probability adding up equal to 1 is called 1 norm, and that's what we are used to with our everyday experience. But then amplitude squared equal to 1 is the actual quantum mechanical mechanism that goes around in quantum systems. And that's how our world behaves. That's just, we can always ask why that is the case, but really our world behaves in amplitude squared equal to 1 way. If you want to read some literature, there are some links here in the slides you can go into. Is more mathematical. To finish off, I want to give people an idea of what's coming up. I think we are pretty much done. I don't want to give too much physics because this is a quantum computing class. We have a lot of other interesting problems that we want to look at. So theory about physics, I would talk about entanglements next. But then we'll start looking at some computational theory. So how do we use the qubits and how do we form gates to manipulate the qubits? Then we can look at algorithms. We have to know about the algorithms in order to understand more about the software, why it is useful, why are we using quantum computing. I think using that, we understand why we're building computing, then we can look at hardware. But I know that there's a lot of interest in this audience in hardware, so maybe we'll move the hardware a little earlier. But I think we need to build up some of the fundamental understanding about quantum mechanics and quantum computing in order to see how hardware is made. So I would give some high-level description of different types of hardware in some near future classes. So the time passes very fast. I will stop here and I would answer some of the questions here.